Yeah, anybody who had a question about this from the end of last class? Can you say where you got confused? Or up until which point you felt comfortable and maybe everything after that you were a little lost?
Yeah, hello.
Yeah.
Yeah, I understood the like when you were explaining it with the graph, but when you got to the formula part, I just could not follow along.
Okay.
Like explaining how the graph relates to the formula, I didn't understand.
Got it. Okay. Good. So, do you understand that this in green? This is just if you look up in like a textbook or online what the general equation is for the normal distribution. It's this thing. So it's defined by the mean on the left and the variance on the right. So that's where its peak is and how fat it is. Um, so this is a function that takes these two parameters and it's written in this way. So there's a lot of stuff going on. Square roots, squares, e's, negative exponents. And I think that a lot of people, when they look at this, they just think that it's just a bunch of numbers and I'll just plug things in and somehow magically things draw a nice curve. And what I'm trying to get across with the idea is where these things come from. In particular, on the top there, we're going to be keeping this. This is for the red curve. We're keeping this, we're keeping this. That's it. Because the mu is equal to 0, and then the sigma squared is equal to 1. So if you plug in 0 for mu, and you plug in 1 for the sigma squared, then it's saying that to draw this red curve, you use this equation. So algebraically, do you understand where at least these numbers come from? You don't have to understand
Yeah.
exactly. Yeah. Let me get rid of these things. Okay. So what I was discussing at the end of the last class is how this part. How. Oh, why? So I was trying to explain why this collection, like it using an e, negative exponents, how does this, if you graph it, how does it produce this curve? So there's three components to this. There's the x squared. So we see an x squared here. We see e to the negative something. And then we have this 1 over the square root of 2 pi.
Yeah.
So if you look at e to the negative x, if you take e to the x, it looks like this. E to the minus x is a curve that looks like this. Have you seen the graph e to the minus x before?
Yeah, we did it in the last class.
Yeah, I mean outside of this class. Have you
Oh,
seen it before?
I'm sure I've seen it like in some math class a while ago.
Okay, so this is what e to the x looks like, and it's pretty good. I mean, we want a curve that looks like this. So this is kind of the way there. I mean, if it, had a peak, if it had a peak and was symmetrical, then in this sense, the e to the minus x is partly getting us there. It's getting us this sort of nice curve on the right-hand side. But then things go crazy when you get close to x equals 0. This just shoots up to infinity. So if you take e to the minus x squared, then it has the effect of making this thing symmetrical. I'm sorry, wait. Ah, sorry. That's not quite right. I can see why people might have been confused. E to the minus x is like this. It flips. No, it is rotation. Whatever. No, it's a flip. Flip. So if you take this, this e to the x, and you take e to the minus x, it's just like it's like looking in a mirror about the y-axis. Things just flip around it. So this is part of our curve. Like, we're happy with this. This goes off down to infinity. What we want is for that to be symmetrical. So we'd like sort of, if this is e to the x, and then this is e to the minus x, then when they're both taken together, then you get this sort of hill look. So that's why you take the exponent. First of all, you take e to the minus x because you want the right-hand side, everything on the right of the y-axis, to have a certain shape to it. You take that and you square it because that will make, instead of things going up to negative, or instead of this line shooting up to infinity, it will match more what is happening on the right. Because if you square a number, if it's a negative number, then you get a positive number. And so the result is you get something that looks like this, where this would be like e to the minus x. Is this making any more sense?
Yeah.
Okay. Great. So then I'll ask you, if you were to take the integral from minus infinity to infinity of e to the minus x squared, you would get the square root of 2 pi. Okay, I'm not asking you to actually derive this, but if you were to, then this is what you would get. You'd get the square root of 2 pi. And this is taking the integral from minus infinity to infinity is calculating the area under the curve. But for a probability distribution, what did we say has to be true about the area under the curve?
It has to equal 1.
It has to equal 1. So if this equals the square root of 2 pi, how can you get that to equal 1?
I guess dividing it by the square root of 2 pi.
Yeah, divided by the square root of 2 pi. And then that way you get 1. So that is each part of this.
Okay.
Does that make more sense?
Yeah, I get it.
Okay, great. Thank you. For anybody else from last class that had questions about this, Is there still somewhere you're lost? I mean, you can. Oh, go ahead.
For the final, would we need to I guess memorize this formula, or probably not memorize it, but like I don't know, do we need to know it like I guess through like moving forward?
You wouldn't have to have it memorized. Generally, for things like this, not for like this. Knowing, conditional probability. What's the probability of A given B? That's something that would probably be good to just know, but hopefully it's not memorization. For this, I don't expect people to memorize the normal distribution, or what the equation is. If you use this a bunch, sure, fine, you'll memorize it just because you use it a bunch. But if not, it doesn't matter. If given to you, can you look at it and sort of understand what's happening? And this e to the minus x part, that gives you the e to the minus x squared. That gives you the bell curve shape. But the area is wrong. So here you have to correct the area. That's what this whole term is doing. The mu here, that will shift the graph left and right. And the sigma squared in this way will give you how fat the curve is. Yeah, I mean, I think it's a good thing if you can look at an equation, maybe not memorize it, but just for later on in life. Like if ever you see this, it's not just magic. It's not just like random symbols. There's a reason that you can kind of picture behind it. This part gives, again, the curvy shape, and this part fixes the area. As far as why the square root and why is this thing squared and why is this one squared and in the denominator and all this stuff, that's to make the calculus work out. We could walk through the calculus, but this isn't a calculus class or anything. Like, I'm not getting that deep into any of that stuff.
Professor?
Yes.
You said that both sides should be perfectly symmetrical.
Yes.
But also you said that this one kind of shift. If belt is shifted, it's not perfectly symmetrical, right? Like it's always like perfectly symmetrical, or
yes.
It's not perfect? Yeah.
So let's take this one. I'll try to draw it symmetrical. So
this is going to be 2.718, right? If 2.718 is going to be half the same. That's called perfectly symmetrical.
So for the normal distribution, this is the normal. So here it's centered, mu is equal to 0. And the width is,
Oops.
Oh, sorry, my application just crashed. Okay. Oh, do I need to reshare it? It looks like it. All right, so for this, the area is 1, and it's centered. And this is symmetrical, right?
Yes.
Okay. So this one is 1 over 2 pi sigma squared. So now I'm actually going to write it, the square root of that, times e to the minus x, yeah, whatever. X minus 0 squared all over 2 times 1 squared. Okay? So far, so good? Oh, just to make this very clear, this area is 1. All right. Now you're asking, if you shift it, will these things remain 1?
Yes, if shifted in both sides remain the same, or shifted, when you shift it, the size not going to be the same.
Okay, so let's say if I shift it, I'll shift it to the right 10 units. So I'll make the mu equal to 10. All right?
Mm-hmm.
So if I shift this, well, what's the best way to do this? Why? Is it not symmetrical anymore? Now, this is minus 10.
It's symmetrical, right?
Yeah, it's still symmetrical. That's right.
Oh, still okay. Oh.
Yeah. So shifting it is literally that. I mean, it's taking it from one place and just shifting it. I mean, nothing changes about the area underneath it.
Oh, area, nothing changing. I got it. Now
Yeah.
I got it. Okay.
And then if you change mu, it just does this. Just makes it thinner, but oh, sorry.
If make thinner, that's not mean that's still perfectly symmetrical, right? The same.
Right.
size.
Yeah, it's still perfectly symmetrical, but this might go up, such that the area is still 1.
Yeah. Now I understand everything.
Okay.
Yes, thank you.
Sure. Let's see, so now this would be 10. And so for the most part, I think this is plenty. This is plenty to know about the normal distribution. One nice thing about it, again, is that you can really just talk about this one, this red one, and then you can shift and squeeze to make everything that one, analyze it, look at its properties, and then shift it back. The other nice thing about it, and I don't know if we'll have time to get into this exactly, but that if you sample from a distribution, and you sample again and again and again, and then you take the average, and you plot where the average is, what the average number that you got is, and then you sample again and take the average, and then you plot it, and then you sample again and take the average and plot it. So the plot is the average of averages. There's one of the biggest things in probability and statistics is that everything goes to this. If you look at the average of averages, all distributions will end up looking just like this. They will end up being the normal distribution. Which is a really surprising thing, because you could have very complicated distributions like this one on the right. But if you sample it many times and take the average, and then you take the average of those averages, then somehow this thing on the right will look like this. So it's not the same distribution, it's the distribution of how far away you are from the average, on average. So that's another thing. That's called the law of large numbers, if you've heard of that before. I don't know that we'll have time to get there in this class. Yeah, if these things interest you, then you can go a little bit deeper in probability or statistics. But Yeah, none of these things are hard. They just kind of build on each other. Fine. So that's about, for right now, as much as I want to say about continuous random variables. Before I move on, let me give you guys another chance. Do you have any other questions about this? I mean, this curve just ends up showing everywhere. So I've already talked about 2 different ways it shows up. There's another, at least 2, we'll be talking about in this class, but can you give an example of the question that you would ask on a final related to this? Hold on. I thought when you divided the power, it expanded the curve, the fatness. Would dividing it by 2 make it fatter than 1? So, no, it doesn't. In fact, that's why you have the 2 here. You have the 2 here. How to say? Let me move down here really quick. So he's saying you have e to the x squared. And so that will look, I mean, that has kind of the right shape to it. So why divide by 2? Or what effect does dividing by 2 here have? Why? So, 1, you can think about this as e over x squared over 2. So, by dividing by 2 here, that makes this exponent smaller, and therefore raising e to that power, raising e to a smaller power, is a bigger number, because e looks like this. So if this is x squared, then x squared over 2 would be here. So that's a smaller number. Therefore, e raised to that power is, oh wait, hold on, let's see. Right, so then e is a smaller number, right, but 1 over that does make it bigger. Yeah. You can get rid of it. You can get rid of the 2 there. But it will just, you'd have to change the denominator here, what you divide it by, or you multiply by, this constant would change. Basically, if you put a 2 here, it makes this left-hand side look a little prettier. But if you integrate this, no matter what, the values are for mu squared and sigma, it will always equal 1. You can try it in Wolfram alpha or something. Can I give an example of a question that I would ask related to this on the final? So, it would probably be something about p-value, which we'll be talking about later this class. So p-value is looking at a normal curve and you're measuring the area underneath it. We'll talk about how to do that without calculus, but you could do it with calculus and think about it as the area under the curve. The way we're going to go about calculating it is a little bit different. But the reason why the p-value means anything is because of the interpretation that it's the area under a curve. So if the p-value is small, then you quote-unquote reject a hypothesis. So there's no evidence for something if there's a small p-value. If there's a very big p-value, then it means that it's probably not an accident, and therefore something is happening, as opposed to nothing. Yeah, I might also ask some questions about, when we do linear regression. Like I said, this thing just shows up everywhere. So when we talk about linear regression, one interpretation of it is in relation, is not as fitting a line through points, but it's trying to find this type of curve. I won't ask you to find that curve, but I might show different graphs and ask, is this a good case for linear regression? Let me give you some examples. Linear regression, good. Linear regression, bad. What I mean by that is, depending on your data, sometimes linear regression will give you reasonable results. Sometimes it won't. So here, this is when linear regression works well. This is when it works bad. There's something a little bit more complicated to the one on the right. Depending, linear regression could be good for this. But the reason why it's bad is because it's not a straight line. That's not a linear function. Loosely speaking, I would like to get to the point where, depending, you still could find graphs like this using just a linear model, which sounds funny, but it's one of the reasons why linear regression is so powerful. Even though it's simple, it can actually do quite a lot. But as far as interpretations go, if you have points like this, you could also find a good fit line through them. But linear regression is, not good in this case. That's in the bad category. Yes, you can find a good fit line, but it doesn't really explain the data very well. In particular, why is there this empty gap between these 2 points? And so on this line, without thinking about the axes, let's see if I can just do this. Imagine a whole family of curves like this. And each of these curves have some mu. They're all the exact same. Sorry, it's a mu. So all of these have the same mu, and all of them have the same variance. So this is the same curve, and underneath the curve are points. So this is sort of something to picture in 3D. Okay, so it kind of looks like a tunnel, right? Like if you're looking down a tunnel like this, then that's the way to think about this. Here is the entrance of the tunnel. It has a certain shape. That exit of the tunnel has the exact same shape. It's just shifted down in distance. So in the same way, you can imagine the points as lying on the road, not above the road, on the road. And when you do that, for any slice of the road, like right here at the entrance, the points should follow this normal distribution. That is to say, if you took any slice, it should look lots and lots and lots of points near the mean, and then slowly sort of thinning out. So here, the probability of seeing a point there is high. The probability of seeing a point here is low. One slice, e.g., just the entrance to the tunnel. Is this picture making sense anyway? Maybe I've lost everybody. Okay. If you have a question, please ask, but it would be something like this. So I'm not asking you to do calculations. I mean, you can have a calculator if you want. I don't think it will help. Generally, the questions that I ask should not require any kind of computation. You can just write numbers, and if you need to type them into a calculator, just leave the numbers as they are. Don't narrow it down to one number or anything. Just make it easy on yourself. I try to ask questions that are more conceptual. So here, one example of a final exam question might be, is linear regression appropriate for this graph, or for these points? Is linear regression appropriate? The answer is no. And if you're looking at it from the line fitting perspective, then that might be confusing why. But from this perspective, it's because these points don't lie on a normal distribution. Let me draw a bunch of slices of the tunnel. So there's the entrance. Down here, there's the exit. And then there's, a bunch of tunnel in between. Okay, so now kind of picture that in like a 3D kind of graph. Well, these 2 points here, these 2 lines of points on this slice, these 2 points just correspond to the entrance of the tunnel. And that does not look like this. You would expect a big clump of points in the center, right underneath the top of the tunnel. Here, you do not see that. At the top of the tunnel, it's empty of points. And so this curve doesn't explain these points very well. And it turns out that these are just 2, if you fit a line, if you find a best fit line in the way that I described, it's doing the exact same thing as if you have a completely different picture in your head, and you're not thinking about lines, you're just thinking about these curves and normal distributions. And you can get the exact same answer every single time, which means that they're really doing the same thing. It's a strange kind of wonderful thing that happens in science and math, sometimes, where you have 2 completely opposite, 2 very, very different pictures that each give you the same answer, and so therefore there's actually some relationship between them. Here the relationship is kind of like this, that if you're thinking of it like a line, it's a line that passes through the points very closely, on average, as close as it can. If you look at it from this perspective, you're trying to find one curve that then you can drag through space, such that the points underneath them are basically around the mean. In fact, the mean here is this line. The variance is another parameter, but the mean, this line that you see here, that's the line that would be underneath the peaks of all of these curves. Underneath the peak is where basically what the mean of these are is the line. So this line sort of defines a whole family of curves. And it's a family of curves because, again, it's not just one curve, it's many, many, many curves that create abstractly something like a tunnel. Like there's not gaps here. There's an infinite number that go on forever. So it would be some question like this, maybe, or maybe something to do with p-value, right? I ask about the area under a curve as it relates to p-value, something like that. But I think without having kind of a picture of these things, or if you're trying to look at this equation here, like how do you make sense of this at all? It's just a bunch of random numbers. I had a plate of food and I threw it at the wall and it just made a big mess. That's sort of what it looks like. But hopefully not now. I mean, this is the second time I'm covering it. Yeah, it's not magic. In fact, you can derive it yourself pretty quickly. Just doing these things. Okay. So, I'll quickly show you what we're going to be doing in Excel. I'll go through it, so this way you know what the steps are in Excel to get these. But this is just a very simple example that I wrote out by hand. There's a bunch of points. That's 1 point at 1, 1. Here's another point at 2, 3. Point at 4, 3. Whatever. And then drawing a line through them. So this is the best fit line. Best fit linear regression line. But why? Why is it? Or, yeah, so we'll go over this, as well as if you do just the regression, it will give you all this stuff. So how do you understand this? What is the multiple R? What's the R squared? ANOVA, we'll talk a little bit about this. Yeah, these things, the coefficients, standard error. We're not going to be talking about every single one, but, 60 or 70% of this stuff. So just what does this mean? And that's pretty much today's class. Oh, I'm sorry. I see it now. Share. Yeah, so I opened up Excel, but I forgot to share it with you guys. Okay, so this is what we'll be making. Okay, so here's a graph. First, you just take some text data. You draw it as a bunch of points, and then you find a best fit line. So I'll show you how to use Excel to go from these points to this kind of graph. But this is something that just Excel does for you. It just gives you this line. I mean, because it's computing it. When I say the theory will be showing how that's computed. And then also you have all of this information that comes out about the regression. So these are, it's okay to have a visual picture like this, but there's a lot of numbers that can be associated with it that can be helpful. So we'll talk about some of these. R squared, observations, the regression, the residual, this df, sum of squares, these coefficients. Here's the p-value. And these things. In fact, all of this here, all of these numbers relate to thinking about it like a normal distribution. These make sense, thinking about it like line fitting. Okay, so you have to shift your perspective depending on what numbers you're looking at. So we'll explain what each of these are today. Okay, so yeah, any questions about that or anything else? Otherwise, I think we can take a break and then come back and pick up from working with Excel. Okay, I'll take your silence. That's fine. So let's come back at 3:10. Thanks, everybody. Thank you. I've started the recording now. These are the underlying parts of the equation, mainly these two coefficients, the intercept coefficient and the first coefficient. So what this is saying is that the line that's drawn is y equals 0.7 x plus 0.8. That's the line. So the slope is 0.7 and the y-intercept is 0.8. Okay? We'll come back to this. We'll do it by hand one time, just so you know the math behind it. But Excel is doing all of the math and returning to you the coefficients. There's these scores that will only make sense if you understand the underlying math, so we'll come back to this. And the same thing with the p-score and these other things. Right now, the only thing that will make sense are these, the coefficients. So if you want a scatter plot, you highlight all of the data, and here, insert. And in charts, there's this, a scatter or bubble chart, and we're going to just choose this scatter plot. Okay, so these are the points. This point here is 1, 1. That's this row. 1, 1. This point here is at 2, 3. That's that coordinate. This one at 3, 2. That's that point. 4, 3 is this point, and 5, 5. So these are the 5 points. Now they're just on a graph. If you want to draw the residual, you take any point, right-click, and add a trend line. There's different trend lines that you can draw. We're talking about linear regression. So there's more types of regression. I might cover some of these our next class, not this one. Right now we're just talking about the most basic kind of linear regression, which is drawing a straight line. So there you go. Now you have your graph. You have this data about the line itself and its relation to the points and the relation of this line sort of in from the perspective of looking at this from a normal distribution family. Okay. So that's it. I guess that's more of just sort of a tutorial. Again, the link that I sent should cover all of that. You guys all sound like that you have familiarity with Excel. How do you get that data again? This data here, the summary output? Yeah. So you go to whatever sheet has your data, and actually you don't need to highlight anything. You just go to the sheet. Under the Data tab, there's this Data Analysis tool. Click Data Analysis, and you choose Regression. And it will want to know the Y range. So I'm less familiar with Excel. I mean, I work more in other programming languages, but here, the Y range, this is choosing B2. I'm not exactly sure why the $2 signs, but $B, $2, that's this. And colon, so choose all of them all the way up to B6. And the X range is similar. It's just here. I guess you can type it, or maybe you can do this and drag it and whatever. And that's it. Click OK. Oh. What did I do wrong? Oh, I see. The X range I chose wrong. There you go. There's that data. It scrunches this, so I don't know, if you double click on these edges, it will expand to the widest thing. I don't know, I like that better. I think it looks cleaner, but whatever. I'll put in this chat. This is from the Excel analysis tool pack, this data analysis thing here that talks about what this regression is. It says that the regression analysis tool performs linear regression by using the least squares method to fit a line. We'll be talking about the least squares and what the math is behind it. It's really not that hard. You can analyze how a single dependent variable is affected by the values of one or more independent variables. Here, the independent variable is the x-axis, and the y is the dependent variable. So for example, you can analyze how an athlete's performance is affected by age, height, weight. Yeah, so given this trend line, you can now make predictions about data that you haven't seen. So if yeah, if I wanted to predict, you know, what the value is at 6 here, or what the value is at 10, then I could just take this line, and we already know what this line is. It's this one. So at 10, y would equal 7.8. And that would be the prediction according to this line. So out here at 7, 8, 9, 10, it would be up here somewhere. If I expanded this graph. Okay, so that's why people do linear regression, because hopefully there is some relationship between the x-coordinate and the y-coordinate. And if there's a relationship, especially if there's a linear relationship between the two, then linear regression is perfect. So you can do things like predict, you know, the x-axis here could be age, and the y-axis could be how much money they earn, or the x-axis could be I don't know, the day of year, and the y-axis could be the price of a stock. The x-axis could be the, I don't know, daily number of cigarettes that people smoke, and then the y-axis could be the number of people who have kind of cancer, whatever. How would you show the variance off that line? How would you show it? Kind of like this. I mean, that's the variance, the r squared. If you wanted to overlay this with my sort of tunnel description here, Excel doesn't do that. You could probably do that in something like Python, but not Excel. Not that I know of anyway. I've never seen that. But if you just want the value, then you can do that. Oh, that's nice. Whatever. So I was trying to get back to being able to modify this. Okay. Fine. So now you know how to do this in Excel. I've already assigned a homework, and it does not include any Excel problems. But if you want some practice, and I encourage you to do that, try to get some real-world data. Kaggle, Kaggle, is a good place to get free data. Or really just, I mean, any small-ish size of data. And if you can use Excel to draw the graph, to get this summary, and then explain if there's a linear relationship in y. So part of that will be explaining what these coefficients are, the p-value, and probably something about one of the r scores. Then I'll give, I don't know, like an extra 10 points or something on for the final, like for the final exam. So if you turn it in anytime, well, I guess by the time the finals do, then I'll give some extra credit for that, but I'm not going to make it anything required. I think it's really important to get both practice with the theory, working with the math, and working with an actual tool to realize things. Okay? I'll make an announcement about that in Blackboard. All right, so that's enough of this tutorial. Really quick, because now I want to go into the math behind it. It's not very much. We'll be able to finish it today, no problem. But any other questions about Excel? No. Yeah, so Excel, it seems probably fine for small data sets. I imagine for large data sets, it works very poorly. But whatever. I mean, that's okay. The more important thing is having a tool to try things out where you can actually play around with data, and I encourage everybody to do it. Linear regression theory. Okay, so actually, I already did some of this here. Yeah, I'll just continue this. So, from the line perspective, drawing a best fit line, not the normal distribution, but from you're drawing a line. From that perspective, intuitively, it's that the best line is the one that, on average, has the shortest distance to all of the points. So here, even though this green line passes through 3 different points, it could be a worse line because it makes a big mistake on 1 point. So that big mistake, even though it has 0 mistake 3 times, that could be bigger than the mistake that the blue line makes on every point, but the sum of these together is still shorter than the error made by the green line. Let me go back here. You'll notice you could have drawn a line. Actually, let's do it real quick. I'll use that same thing. So we have 1, 1. Let's do 2, 2. Let's do 3. 3, 2. And 4, 4. And here, 5, 5. Great. So here, this is the best fit line. You'll notice that it doesn't touch any of the points. So the reason why this is the best line is because if you were to draw the line y equals x, then the distance from that line to this 1 point would be bigger than this distance plus this distance plus this distance, and that distance. So when you sum up the distances from this line to each of these points, it's actually smaller than 1. I can confidently say that because the distance between the line y equals x would have a distance of 1. So this is something smaller than 1. Okay. So the error is what does it mean to be the average distance? Well, it's not, I mean, the average distance, it's actually, divided by the number of points. So without that squared there, this is just an average, right? This is the average error. This is the error of the line to the point. So that's maybe this line here. That's 1. And for all of those, you sum them up. That's what this is. So for all of the points, you consider the distance of those points to the line, and then you divide by the number of points, so you get the average. You square the... Okay, so first of all, I want to repeat that again. This is called the mean error, but we care about the mean squared error. This is the mean error because it's the average error. This is the error on 1 point. Come up with the error over all of the points and divide by the number of points. That gives you the average error. You square it for a number of different reasons. One way to think about it is that it gets rid of negatives. So one problem would be if here's like this. Let's say this is a y equals x, and I don't know, this is 3, 4, and this is 4, 2. So that has a distance of 1 from the line, that has a distance of 1 from the line. But if you do the line minus the point, then the line here is 3, 3 minus 3, 4. And that's 1. I'm sorry, that would be... Sure. Here, though, if you take 4, 4 minus 4, 2, this would be minus 1. So this isn't 1 here, this is like a minus 1. And so if you sum them up, then they cancel each other out. So that's no good. You don't want negatives to matter. So you can square it to get rid of negatives. That's one reason why we have it. Another reason is because you penalize the line even more for being away from the point. So yeah, I talked about that here, where if you were to use, you could also use the absolute value to get rid of negatives. But if you square the differences, then it punishes the line even more for being far away from points. The further away it is, it's not just the error, it's the error squared. So those are two intuitive reasons why this works for lines. I don't know if I'll get into it exactly. Let me think. Yeah. So this. view as line fitting. See below. I'll get to this in a minute. So if you're thinking about this as lines, then the mean squared error is the best fit line minimizes the mean squared error. And so the error here is the distance of points to the line. That's the error. And whatever that is, you square it and take the average. So this is one way of viewing this equation. I'll write down the exact same equation, viewing things as a normal distribution. Let me see if I can copy this from before. I'll just redraw it. Whatever. So you can still think about this line as being a best fit line. But now I want you to shift your perspective and think this line represents the peak of normal distributions. It's hard to draw. Okay, so we're going to be taking the tunnel view. All right. So here's our tunnel. And here, I'll draw this even better. See, so this is what I mean, that the line should meet should be directly under the peak of each of these. And you'll notice that this is, that's some value mu. This is mu. Mu1, mu2, mu3, mu4. Where here mu is equal to mx plus b. So the line that's drawn here is a function that tells you at any given point what is the what's the mean of the normal distribution that lies along that slice of this infinitely long tunnel. and find mu such that variance is minimized. So now we're viewing this as a random variable. And this random variable, you can sample it. Every time you sample it, you throw down a point somewhere. So that's what sampling here means. There's some distribution. The distribution is this tunnel. All right? You could have tunnels that are fatter, taller, but all of these tunnels extend out infinitely in space, sort of like this. So the random variable just throws down a point in this 2D space. Can anybody remind me what the equation is for the variance of a random variable? Or just describe what variance means in words.
Is it not the sum of all the differences between a line and a point, and then the absolute value of that over over the line squared?
No. For this, go back to the probability distributions, when we were talking about probability distributions.
Mm-hmm.
And here we have expectation, we define that, and then later we also defined variance. This.
Yeah. Okay. Yeah.
So this is the definition of variance. It's the average squared distance around the expectation. And here, I was explaining that this is a low variance here. This orange line has a high variance because these points are far away on average from the expectation. So, yeah. This is... Okay, so this is the distance from the expectation. You square it, and then you take the expected value. And the expected value is like an average. So around the average here, what is the expected square error? Or what's, yeah, the expected square difference away from the average. It's the average square distance away from the average. You can say in lots of ways. Some standard deviation. How far off from the average? Yeah, it is sort of how far off from the average. It's the squared distance from the average by definition. So you can just go back to what was it? See, all this stuff about probability, this was before we're just talking about random variables and stuff. And this is a definition, right? Definition. The average squared distance around the expectation. The sum of the standard deviation, I guess that might be squared. So yeah, the square root of variance is standard deviation. I think, I don't know. In some cases, it makes sense to prefer variance. In many, many, many other cases, it makes more sense to think about standard deviation. That's a different conversation. But yeah, the standard deviation squared is the variance. Okay. All right. So from this perspective, what we're trying to do is build a tunnel. And there's two things about the tunnel. There's where the tunnel is centered over, and here the tunnel is centered over a line. And then there's also how fat the tunnel is. So we want to find the center such that the tunnel is as thin as possible. Or as tall as possible. Given that it, well, I guess the, it's not as tall as possible or as fat as possible. It's whatever the one in the middle is. So it's not too fat, it's not too tall. It's just the right width, such that the top of the tunnel is lying over some line. So this is actually, it's not just one curve. This isn't just one normal distribution. It's an infinite number of them. Okay, I'm drawing 4 slices of the tunnel, but this tunnel is infinitely long. All right, so this is variance. What's the definition of expectation? Anybody? That's not super great, really? Anybody? What's the average of a random variable? Doesn't seem to bode well. This is the average 1 over m of the sum that the probability of x is equal to little x times x over all x, over all little x in x. Okay, so it's the value of a random variable multiplied by the the probability of that random variable, and you add them together. So this is a weighted sum. Okay, it's a sum of things, and you're scaling each of those things by their probability. Without this probability here, this would just be a sum of numbers. But instead of a sum of numbers, 1, 2, 3, 4, 5, 6. I can sum up these numbers. This probability is scaling things. Maybe I'll take 1/6 of this, 1/6 of this, 1/6 of this, 1/6 of each of these. Right? So I'm rescaling them. And this would equal 3.5. Oh, I'm sorry, actually, you don't need this one over there. Okay, so it's a weighted sum, according to the probability. So let's take this e to the x, and we'll start replacing it here. So with this e to the x, we'll replace it with this, and then with this outer e, we'll also replace it with this. And let's see what we get. So this implies that the variance of x is equal to sum of x and x, probability x equals x. Sorry. First, we'll do this inside one. Now this is the little x. This thing's squared. Sorry, the sum of that. So this is just a number, and this is going to be itself a random variable. And this random variable is going to be squared. So if I call this random variable y, I'll call this y. Then this outer expectation I don't really like that color. That one's easier on the eyes. For this outer expectation, let's get rid of this squared. That's the same as saying e to the y squared, which is the sum of y equal to some y times the probability that y squared equals y times that value of y. How to say this? Okay, I don't want this to get too math heavy. What I want you to be able to at least picture, looking at this, is that this, the expectation minus x, this yellow part, the expectation minus x, the expectation here is the mu. That's what it means to be the expected value. It's the mean. The expected value and the mean, that's the same thing. So when x equals some value along here, you want the mean to lie somewhere. So this is the distance of the point to the line. And then you square it. Why do you square it? Because that's the definition of variance. It's the squared difference away from the expectation. And then you take the expected value of that, which is a weighted sum, which is an average. So that's a sum, and then you divide by some number. Here, you're dividing by the probability, and the probability is uniform along this whole thing. So this, the variance, this equation, or these, are the exact same as this perspective. This is the expected value. This is the little x, and you square it. And this part is the outside expectation. So this is the average squared distance away from the expectation. And that's the outside expectation. So these two, line fitting and building a tunnel like this, are identical. They're just two ways of doing the exact same thing. Okay, let's take a break. I'm sure that you guys might have some questions about this, so think about them and we can discuss after. Let's come back at 4:15. Oh, good. Yeah, I'm glad that that is helping, the visual with the bell curves. Yeah. All right, see you soon. So we've already talked about these coefficients, and these are in relation to the line perspective. In fact, this would be the equation of the line. So the intercept, that's the b in y equals mx plus b. This 0.7, that's the m. Okay, I'll put this here, I guess. That's added by me. This isn't usually there. I'll make it a different color. All right, so that's added by me. Now, p-value and these percentiles, these have to do with the curve perspective. So first I want to talk about p-value. Oh, I guess I should keep this. Okay, so we've now covered some theory. We've covered the example in Excel. We're here now. And I'm going to be jumping to this, the p-value. The degrees of freedom, very quickly, that's pretty easy. Just mention that here. This one, degrees of freedom. Here, in this y equals mx plus b, this has, if they count, I think it's just 1 degree of freedom. Yeah. So here, this is 1 degree of freedom. You could have a different line. For example, this. I'll get into this maybe some more in the next class, but this is still considered linear regression, even though the x is squared here. The linear here isn't talking about the x, it's talking about the m's. So while this one is some kind of straight line, this one, you could have a line like this here. You can have a curved line, but it needs to be linear in the parameters. So this is 2 degrees of freedom. That's the 1. That's the 2. And so long these, the m's, are not squared, not cubed, no square roots, nothing like this, so long they're just numbers raised to the first power, then that's linear regression. And in this case, you would have 2 degrees of freedom. You have 1 degree here, and you have a 2nd degree here. Yeah, anything deeper than this, we'll maybe have to wait until next week. But I want to focus on this, the p-value. Just out of curiosity, have any of you ever heard of a p-value? Or maybe the term p-hacking? Maybe. Okay. Great. P-hacking. This is the p-value. It's widely used. In many ways, it's a useful thing to know, but by itself, it can be a little deceiving. And so the big picture idea of a p-value is that if it's too small, something doesn't work. If it's big, that means something does work. Or at least that's the best explanation. There's a better explanation than nothing. So p-hacking is when researchers will play around with their data, sometimes intentionally, which is horrible, sometimes just by accident because they don't understand what the p-value is exactly, and so they do it by accident, and so they think that their research is showing something significant. This medicine helps, according to the p-value. Sometimes that's not true. Sometimes it is an accident, or there's other reasons. In any case, p-hacking is you need to have a p-value of above 0.5 for something to be statistically significant. And so people will hack. They'll play around with their numbers to try to get the p-value above 0.5. That way they can claim that their medicine works, or they can claim that this effect is real, or whatever. But what is it exactly? Let me add a page. P-value and R squared. So both of these things, I'm putting them together because they come from the bell curve view of things. Rearrange things on my desk just a moment. Much better. Okay. First, I'm going to go back to the first 1 or 2 weeks of class when we were talking about joint probability. There was a question on this on the first homework. There were some questions on this on the second homework about questions about joint probabilities. This is when one thing happens after another, and these are independent events. So let's take flipping a coin. Flip a coin 2 times. So we could have, so we have this space. Heads, heads. Heads, tails. Tails, heads. Tails, tails. And a probability space is defined by 2 things. So here the probability of heads, heads. We'll call this a fair coin. Okay, so this is the way that we were talking about it before. For the sake of this lecture, I'm going to give another sort of kind of graphical way of thinking about this. So remember, sometimes I wrote this like this, with this squared here, where this would just be 1 coin. Okay, and that is equal to the set product, all possible pairings of things. So another way you could think about building this is with a tree, where this is your first flip. You can get a heads or a tails. And on your second flip, you could get a heads or a tails, where this corresponds to heads, heads, this corresponds to heads, tails, this corresponds to tails, heads, this corresponds to tails, tails. And the probabilities here, you have a 50-50 chance of getting heads or tails on the first flip, and then independently on the second flip, you have a 0.5 probability. And the way that you get these probabilities is you multiply. So you take this one and you multiply them. So 0.5 times 0.5 equals 0.25 for all of these. So you multiply these to get this. You multiply these to get this. Multiply these to get that, 0.25. All right, so this is another way of thinking about deriving the same probability distribution. If you like this way, you can use it. If you don't like it, you can forget about it. And we also talked some about counting, and you have some questions about counting on your homework/midterm. Here, for example, the probability of tails is the number of times tails occurred over the total number of outcomes. And here, tails appears one time, and we have 4 possible outcomes. Whatever. Let's get to this. All right. So, definition. Of p-value. Okay. So there's 3 parts to this. The probability that random chance generated the data, or something else that is equal, or rarer. That's what a p-value is. When I was saying, is there an effect? Is this thing due to something, or is it due to nothing? When I say nothing, or that there's no effect, it means that it could have just been random stuff. I mean, there's no explanation. It's just random. Yeah, why did this person get better? Wasn't because of the medicine. It was just because they just got better. I gave 100 people this medicine, 50 people got better, 50 people got worse. So I can't really say that the medicine works. It could just be random. Otherwise, something that is as probable as being random, or it's something that's even more rare than random. So the probability of any of those 3 things happening is what the p-value is. Let's take a bit more of a bigger example. And for this, I'm not going to type all this out. Just paste a screenshot. Okay. So this is flipping a coin 5 times. Okay, so those are the outcomes. So you can get all heads, you can get one tail, the rest heads, you can get two tails, you can get three tails, four tails, or no tails, or all tails, excuse me. And so those are all the outcomes. There's 32 of them altogether. So probability of four heads and one tails. Let me pick on somebody. How about Jelani? Do you have a mic?
Yep.
So what's the probability of this, getting four heads and one tail?
4 heads and 1 tail. We need the 0.5 times. I don't know the would it be 0.03125?
With this. That'll help. So, four heads and one tail. Here is four heads and one tail. Here's four heads and one tail. Here's four heads and one tail. I don't care about when I get the tail. I just care about that there's only one of them in 5 flips.
I'm a little unsure.
Okay. Let's start first with the bottom here. What are the total number of outcomes for flipping a coin 5 times?
It would be 25.
Not 25. You can count them here if you want.
Okay.
Yeah, fewer than 36. 32. Great. 2 to the 5th, exactly. Yeah, so this isn't any 32. This 32 is 2 to the 5th. And it's 2 because on any one, it's either heads or tails, so that's where the 2 comes from. And the 5 comes because you're doing that 5 times. Okay? So how about this? The number of times the event occurred. So this is how many times can you get, or how many different ways can you get 4 heads and 1 tail on 5 coin flips?
I don't think of it like that. This is included, but that's not all sufficient in terms of like if you do the problem. Maybe 5 times.
5 times, good. Yeah. And you can get that 5 either by just looking over here and counting them. Here's 1, 2, 3, 4, 5, all on the left here. Or otherwise, this is also equal to 5 choose 1. Out of 5 flips, you're choosing one place for the tails to be.
Okay.
So that's where that 5 comes from. And for example, here, two tails. This part. This is 5, choose 2. If you count them, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's equal to 10. Yeah, that happens to be 5 factorial or 2 factorial, 3 factorial, which is 5, 4, 3, 2, 1 over 3, 2, 1, 2, 1. These cancel out. This 2 cancels with that. You get 2. And so 5 times 2 equal to 10. Whatever. Great. So,
Okay.
excellent. Thank you. Thank you very much, Jelani. Okay, so that's the probability of getting 4 heads and 1 tail. Now, by the way, this is why I was talking about, or why I spent time talking about counting. There's sometimes when you multiply a number by itself a number of times. There's sometimes when you use the choose function, and then there's sometimes when you use a factorial, as in here. Being able to count in that way allows you to come up with a probability. So that's why we focused on that. All right. So what is the p-value here? There's something else here. And this is a kind of question that I would, you might be able to expect on the exam. Like I give you something kind of simple like this. I ask you what the probability of an event is, and I ask you what the p-value is. Something like that. So what's the p-value? Let me go up here, and I'll copy the definition just for reference, so it's all on the same screen. So this is the definition of p-value. And so I have to make sure not to go past this line. Otherwise, when I export it, it's not going to look good. Okay. Where? Great. Okay, so this is the definition. Who can I pick on? How about Emily? Do you have a mic?
Hello.
Hello. So I'm just going to ask you for one of these. This one. We'll start this. I might ask you for more. We'll see. What's the probability that random chance generated this? 4 heads and 1 tail. What's the chance that you see that just by random chance?
Wouldn't it be... I'm not really sure how to answer that specific question.
So it's just the normal probability. It's the probability if it's a fair coin and you see 4 heads and 1 tail with a fair coin. We've already calculated it here, in fact.
Oh, so it would be number of times the event occurred. So it would be 5 over 32?
5 over 32, very good. Yeah. So this part, that's with a fair coin. This is the probability that you might see 4 heads and 1 tail, just by random chance. Okay, how about this one? Something else that's equal. What that means is, what's the probability of anything else that has the probability of 5 over 32? In this world of events, what's the probability that there's something else that also has a probability of 5 over 32? Is there anything here on the left, any other event that has the same probability?
If it were reversed, would that make sense? Like if there were 4 tails and 1 head? Or are we only going by head?
No, that's perfect. You got it. 4 tails and 1 head. Yep. So that's not getting 4 heads and 1 tail, but it is something else that's equal. So you could, like, each of these 2 events have the same probability. Okay? Wonderful. And I guess just because, how about this one? Which events are rarer than seeing 4 heads and 1 tail, or 4 tails and 1 head?
Would it be like 3 heads and 2 tails? Something different besides the 4 and 1?
Different than the 4 and the 1. So you're saying it's this? I'm sorry, 4 heads and, you said how many? 4 heads and 2 tails?
No, 3 heads and 2 tails.
3 heads and 2 tails. So is this rarer than the yellow one?
No, so would it be like the occurrence of all heads or all tails?
There you go. Yeah. Yeah. Each of these 2, they're even more rare. Okay, so the p-value, it's computed from 3 parts. First, you figure out what the probability is of the event by itself, if it were just random. And random here means there's nothing special going on. That means that this is a fair coin. And then so we have 5 over 32 plus 5 over 32. And so that's the probability of random chance. This is the probability of something else that's equal. And so what's the probability of the rarer thing? What number should I put here?
1 out of 32.
1 out of 32. Why 1 out of 32?
Because there's only 1 chance of it occurring out of all 32.
What is the 1 here? What's the 1 chance? All heads or all tails?
All heads.
Okay.
And then if you want to do all tails, it would be all tails, and so I guess it would be 2.
Yeah. Yeah. You could break it up into 132 plus 132 if you want, whatever. But I'll keep it like this, just to keep it short. So that is some number. In fact, it's 12 over 32, which happens to be 0.375. Okay, that's the number. Any questions about how this number was calculated here? I'll get to in a moment how to interpret this number. But first I just want to make sure that the method of calculating it is clear to everybody. Got it. Okay, great. So this is the p-value of this one event. And it's this number. The p-value will always be between 0 and 1 because it's a probability. And I guess I'll say generally in science or medicine, a p-value less than 0.5 is considered statistically significant. That is to say that this is not a statistically significant event. The fact that you see this is, if you flipped a coin 5 times and you got 4 heads and 1 tails, that should not surprise you. That because it can happen pretty often. It's not so rare. And this is based on the thinking that this is a fair coin. So with using a fair coin, getting 4 heads and 1 tails on 5 flips, it happens, like, pretty frequently. And that's what this p-value is saying. Why 5? Good, very good question. Yeah, why 5? Why not 4? Why not 3? It's just a general kind of bar that says that 95 times out of 100 you'll be correct. There's 1 time out of 20, or 5 times out of 100, where you might be wrong about this. But being right 95% of the time is, that seems significant. You're not right 50% of the time. I mean, you're right 50% of the time if you're flipping a coin and you're saying yes or no. Is it going to rain today? You flip a coin. Yes, no, yes, no. I mean, it'll be about a 50% chance. But if I ask you a question and 95% of the time or more you're correct, then I somehow tend to think that you might know what you're talking about. 80%, for example, that might be too small. Because, yeah, sure, you're right 80% of the time, but that still makes you wrong 20% of the time, and I don't like that 20%. So, yeah, I don't know of a more principled reason behind it than just this. It's, I don't know, people in these two fields feel like that if you're correct 95% of the time or more, you're reliable. Depending on the study and things, they might have a higher or a lower bar, but generally, this is the value that everybody takes. It's a really good question. So one thing that I've talked about in this class, just a general technique, is coming up with a very, very simple example that's easy to write down, and make sure that you understand when things are simple, when the world is a simple place, that you understand how everything is working. Because in the simple case, if you're lost somewhere, that means that you should learn. like where you're getting lost. And because the world that you're dealing with is simple, you can maybe find the error easier there. Correct it, and then you can do more complicated stuff. Another technique is taking a small example that you know works, and you blow it up into something really, really, really big. Okay? So I think that, for example, with the Monty Hall problem, dragons and princesses, having the wizard reveal, or having the knight choose from one of 100 caves, and then the wizard revealing 98 dragons, gives you a better feeling about why changing your mind works better. It's taking the simple example, which now seems difficult, and then you blow it up to make it actually easier. So we're going to do something like that here, and then we can take a break. So yeah, I'll talk more about this after break too, but I want to take this example and blow it up. So here, with a fair coin, getting 4 heads and 1 tails is not surprising. You probably don't have a special coin if you flip it 5 times and you see 4 heads and 1 tail, because a fair coin will do that pretty often. So no, somebody who tells me that they did these 5 flips and got this result, I can just assume that they have a fair coin. Because this number is not small enough. Now, let's see what kind of event would have to happen for somebody to tell me the result of their coin flips, and I think this is probably a special coin. That doesn't sound like a fair coin. That's way too rare of a thing to happen. So now we're going to flip a coin, I don't know, 1,000 times and see 1 tails and 999 heads. Without working through it, hopefully this makes sense to you. Why, if somebody tells you that they flipped a coin 1,000 times, and out of those 1,000 flips, they only saw 1 tails, that something strange is going on. That is not a normal thing. That coin is probably a weighted coin. It prefers heads. Maybe it lands on heads 99 times out of 100. Something like that. That's not a normal coin. That's not a fair coin. If it were a fair coin, it could be. Fair coins, this is something that can happen, but it's so extraordinarily rare that it's easier to believe that it's a weighted coin for heads than it is a fair coin. So I'm rejecting the idea of the fair coin. And I feel comfortable with doing that because this probability of happening with a fair coin is so low. So let's show that with the p-value really quick. I'll do the same thing. All right, so we have these 3 things. Let's calculate it. Probability that random chance generated the data. Well, it's the number of ways that this could happen, assuming a fair coin. Well, there is 1,000 choose 1 ways of getting 1 tails. That's 1,000. Over 2 to the 10, which is, I'm sorry, 2 to the 1,000. My God, that's such a big number. 2 to the 10 is 1,024. Boy, I don't even know. This is it. It's a ridiculously large number. 2 to the 1,000. Maybe I should bump it down. I'll stick to it. Well, so long it doesn't break Google. Let me see if I can actually calculate what that number is. Oh boy. All right. So this is 1,000 over 1.1 times 10 to the 301. Okay. It's a really big number in the bottom. That would be the probability. So this is roughly 1 over 1 times 10 to the 298. It's about that. Let's make it easy. We'll say 300. Okay? It's about that. So this is 1 over 1, 0, 0, 0, 0. That, zeros. How many zeros? 300 of them. It's a very, very small probability. So that's the yellow. That's the probability of this event, seeing 1 heads and 99 tails. Something else that's equally as rare. Well, this is still 100 or 1,000 choose 1 over 2 to the 1,000. This is getting just as above, not just getting 1 tails and 99 heads, but getting 99 tails and 1 head. This is 999 tails, 1 head. Plus anything that's rarer, which are all heads, all tails. So, in fact, there's only one way to do that, but I'll do 2 because you can either get all heads or all tails, and that's also over 2 to the 1,000. So altogether, we have 2,002 over 2 to the 1,000. Let me get these colors here. This is all heads plus all tails. So things don't change that much. This is still, I'll just call it 2,000 over, well, let's see. That's about 1,000 over 2 to the 999. This is still something like this. I'll call it times 10 to the 299. Okay? This is much smaller than 0.05. Okay, it's a ridiculously small number, like a horrendously small number. Your arm would get tired writing out how just writing the number of zeros in the denominator. So that is to say that seeing 1 tails and 99 heads is not something that you should accept as being a likely thing to happen with a fair coin. That is statistically significant. So you should reject the idea that it's a fair coin, and it's more likely that there's a better explanation, like the person is dealing with a weighted coin, like they're lying to you, like I don't know, they flip the coin in a very, very, very strange way where they're inducing it to land on heads somehow. In any case, that's not a random thing that just happened. I mean, sure, it could be, but again, the probability is so horrendously low, there's a better explanation. So this is why this is the idea of taking an example, a simpler example, working out things that feel comfortable, seeing 4 heads, seeing only 1 tails on 5 flips. It's okay. I mean, it's not that surprising. Seeing 1 tails on 1,000 flips doesn't happen for all intents and purposes. So that is a statistically significant event. All right. So just before break, I want to go back here, and we can look at this p-value. So these p-values are not below 5%, and so this doesn't seem statistically significant. That seems a bit weird to me. I'll look back at that. Anyway, let's go ahead and take, I'll say a 13-minute break. We'll come back at 5:20, and I'll finish up on the R squared, and that will be it for today. All right, thanks, everybody. Okay, welcome back, everybody. So, I apologize, I made a mistake earlier by talking about these p-values, which are also p-values. But these are actually a little bit harder to understand because these relate to these two coefficients. They're the p-values that these coefficients are correct. Also, I forgot before that I had updated this graph to make things very much along a straight line, and so I was confused at why the p-values were so high. This significance f, that's the p-value for the line. So this would say that because it's so close to 5, this is very likely a good explanation, but not quite. If this point, actually, let's just play around with this a little bit. So if we wanted to make this more linear, then I could bring this point closer to the line. And then that would make this line more accurate for being correct, because I'll be reducing the error associated with this point at 3.2. So instead of 3.2, let me do 2.5. There. Now I push it up. So this updates automatically. I thought that this sheet did too. It doesn't. So you have to run the analysis again. There. Now we can see that it's a 0.1. So by just moving that 1 point, we went from 0.5 to 0.01, excuse me. So that is to say that this is strongly statistically significant. There's a statistically significant relationship between x and y. Or there's a statistically significant linear relationship between the two of them. If you add points here at random and you look at the p-score, play around with it. Yeah, I mean, just you can take some toy data and just sort of see what happens with these things. So by making this point less of an outlier, that makes this relationship stronger. The fact that this line explains the relationship between x and y. Okay. But yes, I also wanted to say again, this is the significance f. I don't know why they name it like this. This is the p-value of the regression line. These p-values are also p-values, but they're in relation to these coefficients, and maybe that's a little too much for this lecture. Here, I already said that these were the degrees of freedom. I've already talked about that. the residual here, this is depending on which axis. This one is the one that we care about more, the regression coefficient. This is the slope term, or the m term. How many m terms do you have? This is the sum of squares. And this is the mean of the squares. So here, the sum of squares, the reason why you have that is because because of this. You're summing up the squares. It's not giving you the mean of the squares, but you can just divide by the number of points, and then you'll get the actual mean squared error. But that's why it's giving you the sum of squares, because it's related to the way that the whole thing is computed. In fact, Excel, I typed it earlier, or I copied it and pasted it to our chat. It says that the regression analysis tool performs linear regression analysis by using the least squares method. So there's other ways. In particular, there's this way. This is one way. You could solve it. This is not the way that Excel does. Excel uses this way. Same thing, as we know now. Okay, so the only other thing are these. Oh, down here, this is really easy. So there's 4 points. This is what the line would have predicted, and then this is how incorrect it was. If you take each of these and you square them and add them up, then you should get this number. This is for each of these points. Yeah, these lines here. So this is called a residual. A residual just means an error. Fine. The last thing is these. Multiple r squared, standard error, whatever. Here, okay, I'll try to do this kind of quickly. P-value in r squared. Oh shoot, there's one other thing about p-value. Okay, one other quick thing about p-value is how does it work with continuous distributions? Again, this is the area, and this is the confidence interval, a 95% confidence interval. That means given your hypothesis, 95% out of the time, if for example, in this example, if there is a fair coin, 95% of the outcomes should be in this area. It's not exactly fair because this is a smooth distribution. That up there would actually be a discrete distribution. But it's pretty close, especially on 1,000 coin flips. So what that means is that this is what you use to compute the p-value. Well, actually, here, let me do this. So here, the probability of, let's say here, this is the probability of one tail (999 heads). So that would be the probability of that event. And over here, this is the probability of 999 tails and a head. Am I using? Yes. And this is the probability of everything smaller. And we can see that this is less than 5%. This here, starting from this point, is 2.5%. And this here is also 2.5%. Right? 95%, where's the other 5%? Half of it's on the right, half of it's on the left. Okay, so this number is the p-value that we calculated would be taking the area under these parts of the curve. And that is less than 5%. So this is another way of thinking about a p-value in terms of areas under a curve. Areas underneath a probability curve, a probability distribution curve. All right, r squared. Def. R squared. So here, r squared is equal to 1 minus unexplained variation over total variation. Now I have to talk about what variation is here. This is not variance. It's a different thing than variance. I'll do two examples. This and this. Okay, so here on the left, and we'll pick up here again from the next class, but just very quickly here, this on the left should show you that there's no relationship between x and y. There's no relationship, because any value of x that you choose, I could get kind of any value of y. I mean, if y is, if I'm looking at this point of y, well, there's a point of x that has it, there's one, there's one, there's one, there's one. So y does not depend on x, where on the right it does. There's a relationship between the x and the y. Here, let me erase these. Shift this whole thing down. Add to it. Ugh. Okay. So, first of all, total variation. Total variation means you assume that nothing special is happening. So you choose the mean of the data. Mean of all points. Okay, no slope. So for this one up here, that's this. Okay, so here, this blue line is in the middle of all of these points. And here, this line is also in the middle of the points. I mean, all of these points, you can kind of view them as all getting sucked over to the y-axis. And then if they were there, you know, all sitting on the y-axis, then what would the horizontal line be with no slope? That's in the middle. That's what the blue line is. This, the unexplained variation. That's the variation from your hypothesis line, which in this case, it's not a very good one. This may be this line. And there's also variation around this. That's this plus that plus this plus that. I mean, there's these points also vary around the line. And so you take one over the other. Here, it's this. Oh, sorry, actually. It's a bit wrong. That's not the blue. This is our best fit line. And for these greens, that's the variation around your hypothesis. That's unexplained. The total variation is around the mean of the data. Should make this gray. Fine. And this is the total variation. Here, they're the same, basically. Okay, so this is what it means to vary. And here, your hypothesis and the mean are basically the same line. Here, they're very different. And it's 1 minus this. Don't forget the 1. I'll make it bold. So a good R² score is a big number. So here, the unexplained variation is a small number compared to this. And the total variation is a big number here compared to this. So here, the unexplained variation and the total variation are about the same. So that is close to 1 as a ratio. 1 minus something close to 1 is close to 0. So this has an R² of close to 0. R² near 0. This has an R² near 1. So this says that the line is predicting something, that there is a relationship between x and y. Here, there's no real relationship because the variance around the mean of the y's is not explained at all by the hypothesis line. Where here, this hypothesis line, it reduces a lot of these purple ones. Like, look at this purple one here. That's a huge variance for that 1 point away from the mean. But this line does a very good job of explaining it. That's a very small distance of this point to that line. So this line explains why this point is so far away from the mean. Okay, so that is it for the R². Oh, let's go back here really quick. Here, the R² is close to 1, closer to 1. What this says is that 89% of the variance in the data is explained by this line. This line explains 89% of the variance around this. Here the variance would be around this, the line y equals 3. So that's a very good number. These are kind of related, but they're calculated in different ways. Sorry, the R². So that's it. have a good weekend, everybody. Email me if you have questions about homework. Next week, Tuesday is going to be our last formal class, and I will be assigning the final next Thursday. So, and you can turn it in by Friday midnight. Thank you, everybody, and I'll see you next week.